Okay, in this lesson we're going to talk about evidence for the Big Bang. There are three primary pieces of evidence for the Big Bang, or for the inflationary Big Bang model. Those are the cosmic microwave background radiation, the proportions of hydrogen and helium that we find in the universe, and the Doppler effect, or the redshift of the stars and galaxies around us. And that's related to the Hubble expansion law. So in this lesson, we're gonna talk quickly about these three things. The first two of which are talked about in section 1 of this lesson, and the third one is talked about in section 2. And then we're going to talk a little bit about your upcoming project, or just emphasize how you need to figure out this Doppler effect in order to complete your project. And then also talk a little bit about what you're going to find on your upcoming quiz. So, first evidence for the Big Bang is this cosmic microwave background radiation. So to understand this, first we have to understand what is radiation. Radiation is light. But light is not what you think it is. When you have thought of light in the past, you've probably thought of the colors of the visible spectrum: red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv, you might remember. But that is only visible light. There's also a lot of light that our eyes can't see. That includes radio waves, microwaves, infrared radiation, ultraviolet, X-ray, and gamma rays. Those are kind of the main categories of this other kind of light. And as you can see, the radio waves and microwaves have longer wavelengths, and the gamma rays and X-rays have higher frequencies and shorter wavelengths. These are the ones that tend to be dangerous for us to absorb: ultraviolet, X-ray, gamma rays. They're known as ionizing radiation that can actually mess up our skin and things like that. So radiation is light, and we're seeing these microwaves coming at us from all directions, not from any particular star. So normally when you look at a telescope, you look up at some object like the moon or a star or a planet, and you collect or look at the light from that object, and it comes into your telescope. But this microwave radiation seems to be coming at us from all directions. It's as though we're surrounded with something that's extremely cold and is emitting these microwaves, which tend to be associated with really cold bodies. So, if you're the kind of person who's really cold, you might be emitting a lot of microwaves yourself. If you don't have good circulation or something like that. Ha ha ha. So, one way to understand this is to think, well, okay, so great, this stuff is coming at us from all directions. Why is it coming at us, and why is it so cold? Well, it might help to think about a refrigerator. The Big Bang tells us that if we are expanding from this really small singularity, then expansion should equal cooling. And that's the same principle by which your refrigerator operates. We compress air, which then heats it up, and then that heat is dissipated into the room from the back of the refrigerator. You'll see coils on the back of your fridge or underneath it sometimes. And then we send the refrigerant that's cooled down to room temperature back through an expansion valve. So it's still high pressure, but when we expand it to a lower pressure, then it gets really cold. And that's what cools down your refrigerator. So that's the same principle by which the universe would be cooling in a Big Bang scenario. And that seems to be the case. So this microwave background radiation are these waves that have expanded and cooled as the universe has gotten older. So that's the first piece of evidence for the Big Bang. There's also the proportions of hydrogen and helium, and this is just based on the sort of the quantum physics of the extremely early universe, when hydrogen and helium first formed, which would have been about 300,000 years after the Big Bang. The way that would have happened, cosmologists expect there would be about 10 hydrogen atoms for every one helium atom, and that's what we find in the universe around us as we look, although places like the sun are currently burning hydrogen into helium, so the proportion seems to be moving in that direction. But anyway, this lines up with what we expect from the Big Bang. Then there's also the Doppler effect. Now, as I mentioned, this is important to understand, and it's kind of a difficult one. So let's look at the video that's in your text, and you'll see this man standing here, and then this ambulance comes, and it's emitting these waves. And you see how often they hit the man as the ambulance moves towards him. Those are basically like the sound waves from the siren. Now see how rarely they hit him, how much more they're spread out now as the ambulance moves away from him. Now they were still being emitted at the same rate by the ambulance, but when the ambulance is moving towards him, those waves are getting scrunched up because they're being released progressively closer and closer to the one before as that ambulance is moving towards the person. But as the ambulance moves away, they're being released from further away. And this is the same principle by which light behaves. Light waves get scrunched up as an object is moving towards us, and so the light will become a higher frequency. It'll hit us more often. And then light waves, as they're moving away from us, will get spread out more and more, becoming a lower frequency. And this is exactly what we see when we look at the visible spectrum, the light waves. So you'll see that the bluer lights tend to be higher frequency, and the redder lights tend to be longer wavelengths or lower frequency light. And that means that if a planet or a star or a galaxy, let's say this is the Earth in blue here, if a planet, a star, or a galaxy is moving away from us, then the light waves that it emits will be spread out as they come towards Earth. And let me make sure the star is visible here. And whatever it's moving towards, if something is moving towards something, those light waves will be scrunched together. Even the exact same light wave that's being emitted will be spread out, and it'll become redshifted. It'll look more and more red to us. And as we look around at all the stars and galaxies and things around us, we see that almost without exception they're redshifted, which means the light is redder than we would expect. And that means that basically all these stars and galaxies are moving away from us, as though everything is expanding away from everything else. And so the Hubble expansion law actually tells us that the farther away something is, the more quickly it's going to be moving away. And that makes sense if you just think about if this distance between the Earth and this far star is increasing, well, if everything is expanding away from everything else, it's going to be increasing more quickly than this distance between the Earth and the closer star, because these two have to be basically moving away from each other as well in opposite directions. Everything's moving away from everything else. So this star is going to be moving more quickly away from the Earth than the closer star. Okay, so next thing I want to point out is just one question in section 1 asks, what did scientists predict the Big Bang should have left? You'll see this in your lesson. I think that's a confusing question. It makes it sound like, what should the Big Bang have left? As though if the Big Bang did have 12 apples and you took 4 away, then how many should it have left? I think that's confusing. They're not asking what the Big Bang should still have or what it should have left. They're asking, what did it leave behind? What should it have left behind? If the Big Bang is true, what evidence should it have left behind? That's the question they're asking, and that's basically what we've just been talking about. It should have left behind this cosmic background radiation and a certain proportion of these elements we discussed. Okay, and finally, I just want to mention. I do want to mention that the Doppler effect is an important thing, obviously, for you to understand, and you can get more information on that from my website if you check there. But I also want to point out that on your quiz, I've looked at it, and there are some primary things that you're going to find on it. You're going to want to understand the 5 different types of scientists. There were 4 talked about in lesson 1, and then 1 talked about in the last 2 lessons, which is the cosmologist. And you want to make sure you understand distinct things about the 4 theories of the universe. You make sure you want to understand what makes them each distinct from each other. What are their characteristics? Those 4 different theories: steady state, oscillating, the Big Bang, and the inflation theory. And then some key terms that you'll want to understand is the cosmological principle, and again, like I said, the Doppler effect. Okay, best of luck.